Okay, for people who are joining this live stream, this is a slightly different thing that I've been doing the last few weeks. This is beginning to return to my day job of designing Wolfram language, and but still beginning to think about what we can learn from what we have figured out about physics to inform the what we're doing in Wolfram language design. And so the thing we're going to look at today is kind of a particular case of essentially what amounts to distributed computing that I have been thinking about one way or another for 40 years, and I'm so frustrated I haven't been able to figure it out. So let's see whether in the next hour or so we can make progress. All right. What we are looking at is combinators, and the idea here is, let's see, where's our best implementation of combinators that we can play with. The I think we had looked at. Okay, the big issue is, so combinators. Where do we have a good version of combinators here? I think we had the notion of a combinator simplify, right? So let's write down what it is we're trying to do here. So first thing we have is, okay, we're thinking about standard combinators. You know, standard combinators, e.g. SK. But in general, we could have any lambda basically to correspond to a well, what is the general case of what we might consider to be a combinator? Did I lose everybody here?
I'm not sure everybody here knows exactly what a combinator is. I mean, I'm aware they exist, but if you ask me to define them, I would be totally lost.
Well, okay, so look, the special case of combinators that's 100 years old, and due to our friend Moses Schoenfinkel. Oh, I got to show you something. I got to show you this thing. Maybe I already showed you this, but let me see if I can pull it up. Hold on. Oh gosh. Okay, so let's look at the sort of the thing that's 100 years old is this idea of representing that we looked at in, for example, here, where we're looking at representation of where we have these combinators S and K, and we have these combinator expressions like this, and then we are evaluating those combinator expressions as a way to do computation. Make sense? Yep. What is a combinator? So the generalization that I had in NKS was what I called symbolic systems. So let's take a look at what those were. Okay, so those were things which were of the form some head here. Okay, so first question, what is a combinator? Okay, so one possible definition is it's a head with various tentacles. That doesn't sound very appetizing, but okay, so example would be, whether I have clicked a copy here, no, something like E of X blank. Oh, wow, that's weird. Let me actually quit my kernel here to make sure I don't have anything too bizarre defined. Okay, E of X blank, Y blank, colon equals, or arrow, X of X of Y. So in other words, it's something of the form, okay, so it's a head with various curried arguments, I would claim, right? So can Roman, can you speak up, please?
Yes, I mean that's exactly, it's a symbol with certain, there's a single operation, binary application, and there is some simplification or transformation rule whenever that element appears with a minimum number of arguments.
Okay, so a head with curried arguments, but now there are no literals here, right? This is just in the only literal is the head, correct?
Well, in the rule, yes.
Right.
But presumably we could have rules that involve several combinators or that return something with other combinators, etc., right?
Well, I'm not sure. I've never seen
Well,
anything like that.
I think this is referred to as a primitive combinator, as something that's defined by a single reduction law in combinatory logic, and then you can have compound ones, as Jose said, that are because there are two fundamental. Well, there's really only one fundamental operation in combinatory logic, which is application, and so then by applying different combinators to each other, by applying different primitive combinators to each other, you can produce composite ones that are effectively defined by multiple reduction rules, as Jose says.
Okay, so someone on the live stream is pointing out that a combinator is pure function without any free variable, which is, but the arguments are being curried here. So that's another feature, right? This could be, all right, so okay, this is what I'm trying to understand. Okay, so it's a head with various tentacles, i.e., it's a pure in the sense of no external. It's a pure function with a certain number of arguments. I mean, what is the right definition here? Guys, okay. I think the correct definition that we should really be thinking about is pure function with a certain number of arguments. Pure function, no external data, no external dependencies, with a certain number of arguments. Okay, now I mean, in the case of, in the purest case, the only thing the function does is function application, right? It has no pluses or anything else inside it, right?
Yes.
Okay, by the way, for people who are wondering what on earth this has to do with physics, we are going to get to that very soon. Okay, all right. So then, and by convention, everything is curried. Okay, so then we have the standard combinators, e.g. the Schoenfenkel combinators. Okay, and let's just remind ourselves what those combinators actually are. And they should be these ones here, two combinators. Okay, S of x blank, y blank, z blank goes to x of y, z, y of z, k goes to that. Okay, so in our design, I mean, people have defined, like, there's the y combinator, which is a fixed point combinator. There's a bunch of other combinators that can be defined purely in terms of function application, right? Yes?
Yep.
Okay. All right. So then we've got combinators like these ones here that are like, these are the Church numerals where we can define 0 is this combinator expression, increment is this combinator expression. Okay, so then when we want to get 2, we just say increment of 0. And we get that, presumably. Now, I don't know whether that's in simplified form. We have to, this is where things start getting interesting. Oops. Because now we're applying these combinator rules, and in that particular case, it did nothing. But presumably, if we apply the power combinator, let's do that. Let's define the power combinator here. And we say power of, presumably, let's say 2 to the 3, for example, right? We should be able to get that with this here, if I'm not mistaken. Yes? And now, this thing, however, if we reduce it...
Do you need to use it in curry form?
I absolutely do, otherwise it doesn't have a hope. Okay, so that should be, so we need the combinator decoder here would be, so this should be 2 to the power 3, right? So let's see whether that is 2 to the power 3. We can say nest of increment on 0, 6, 2 to the power 3 8 times. Okay, why isn't this not equal? Did I get something wrong?
I think we have counted that last time. I think it only collapses if you then apply it to something, right? I mean, 0 by itself represents 0 times application of a function. So to actually do something, you have to say 0 of f of x.
So you claim that we have to do what we have to do is this applied to, let's say, k, for example. Do you believe that?
Yeah, and one more. So this is 8 times applying k, and now you have to apply it to something like x or so. Yeah, okay, yes. Okay, yes. So that is correct, right? 8 times application of k to k.
Yeah, all right, okay. 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 All right. So the thing that comes out then is a power is a function then.
Numerals are carried forms of nest, right?
Yes.
Twice carried. Nest of n applied to f applied to x gives f n times of f of x.
Okay. All right. I believe you. Okay. Now let's see where things start to get really hairy. Okay. Because let me look at this. Let's see. Okay. Let's look at. I'm trying to find a case where things start to go really crazy. So what we've got, the big issue is it going to terminate upon combinator reduction, right? So if I do this, it goes away for a very long time.
By the way, the question of whether pure S terms terminate is decidable. I just learned that recently because I met a former colleague of mine who wrote his PhD thesis about S terms about 2 years before me with the same thesis advisor. And so at his 90th birthday, we all met, and I asked him, and he said, yes, it's now settled. It's decidable whether these S terms terminate or not.
Okay, well, that's interesting. I mean, but let's understand what's going on here, okay? So the main issue is, and we need a way to represent what's happening, and this is where things are going to get complicated, right? This thing, let's say we say nest list of this, applying C rules to this, right? Okay, this is where things get really hairy, right? Because what's happening here is this is, God, what a horrible mess. Look at this crazy thing. Okay, so let's look at that, and let's look at how do we figure out what we want to say leaf count to get the sizes of these expressions, right? And let's say 50 times. Maybe getting huge. Okay, so this is getting to be 24 million, an expression of size 24 million. Okay, so the question is, does this terminate or not? But the more interesting question is, what's the correct evaluation order? Because what happened here is we've got this expression, and it's essentially got this evaluation front of where is this substitution actually happening. Am I making sense? Because there are many different ways, right? It could be the case that one evaluation order does not terminate, but another one does.
Yes, I mean, this is, for example, typical with combinators that involve k, because k swallows arguments. So if you simplify k before the argument, it goes away. But if you go into the argument, it may never terminate.
Okay, so why is this relevant to anything? Okay, the issue is what's going on here. What we need to think about is essentially an evaluation front. otherwise known as, and this is where I'm hoping we can make a multi-way system out of this and try and understand what it's doing. Because the different evaluation orders, the different reductions are like, picking different updates in the multi-way system. Let's give another, the other analogy we've looked at before is recursive evaluation. So let's just look at the cases here. Cases of evaluation control. Okay, so one case is combinators, e.g. combinators, where it's a question of basically where it's / dot, repeated repeated substitution. What do you substitute first? Right. Another case is e.g. Recursive definitions, like f of x blank colon equals something involving f, something like this. What do you transform? What do you evaluate / transform first? Yes. Now these two cases are clearly very similar, right? Although they may not be. In this case here, in the case of the even the factorial case, right? We have an issue there, because if we are just doing this in the most default way of doing this, what we will have, so let's do this with an arrow here. Well, that's actually not going to work correctly, because this here, if we do that with an arrow and we say nest list hash / dot that ampersand f of 10, comma 15 or something, we will get that, right? But in actuality, if we were to evaluate this directly with assignment, it would not do this, because it would never notice that it's getting 0 times some number, because it would just keep drilling on the f. Am I making sense?
Yeah, in Combinators, you don't have these extra operators that may simplify, right? So.
No, I understand. What I'm saying is, the issue here, what I'm trying to define is, there's an evaluation front, right? Like imagine we're doing Fibonacci, okay? There's going to be a tree that's generated, and there will be an evaluation front that says what to do next. Am I making sense?
Yes, certainly.
Okay, so my big question is, how do we parameterize that evaluation front, right? And my claim is that the parameterization is just like the parameterization of reference frames that we've had to do in physics. See what I'm saying? So let me be more specific, okay? So let's say we go, I don't know whether people have, let me see. Let's say, I'm trying to find the relevant place. Anybody remember where this is? I think it's, how do I discuss this? So that's it. No. Come on, where is it? Anybody know this well enough to know where it is? I'm trying to remember where I had a nice set of pictures of, I wonder whether searching works here. A nice set of pictures of eek. That's not where it is. This is where it is. Okay, all right. So think of this. This could be a recursion. Yes, no, maybe. This is a set of evaluations that you're doing. In this particular case, it's gotten from the successive string rewriting, right? Do you get what I'm saying?
Yeah, could you, for example, Fibonacci, where you always have to do 2 and the middle ones combined?
Yeah, I think so. I think this is like Fibonacci, except the tree doesn't happen to have this shape because it's a Fibonacci tree, so it has slightly different shape, but it's the same idea, I think. But the issue is, this is the standard depth first way of evaluating the recursion. Yes? Actually,
yes. I mean,
right. Okay. This will be some kind of breadth first scan, right?
mm-hmm.
So now, when we think about foliations, right, what we're doing there, how do we think about this? This is what I'm trying to understand. How do we think about this parameterizing this, breadth first, this depth first, all these other complicated things? Many of them are incomprehensible, frankly. They're weird orders. But then we have this notion of a reference frame where we are providing a foliation that is some kind of very organized ordering of the evaluation. That's what I'm hoping we can figure out, is how to parameterize sort of organized orderings of evaluation. Anybody following?
I don't see why this should be done in an ordered way. I mean, cannot be just any one and then any other one. I mean, this looks like you need a position argument to say, act on this specific one.
Well, okay. So the question of whether you can do it in any order is essentially a causal invariance question.
And the answer is no.
In general.
Well, combinatory logic is known to be non-confluent. There are Boolean extensions of it that are known to be confluent, but standard CL is not.
Even for the SK combinators?
Well, the SK combinators are universal, so yeah. Well, SK and I are universal. But so, if you take combinatory logic and you essentially adjoin Boolean constants, then it was a fairly recent result in logic that that system is confluent and complete, or terminating and complete, I should say.
Okay, so wait a minute. So first statement is, okay, so the claim is that combinators on their own. Okay, the first claim, which I just want to remember here, is termination of S combinator combinations is decidable. So is it obvious, but by which you mean that there exists a path by which the thing can be made to terminate? Is that correct?
Well, no, I mean, you can tell whether it terminates or not. And essentially...
No, but there could be an evaluation order where it doesn't terminate, even though, is that correct? Or does it have to terminate for all evaluation orders?
I think because what I understood, I mean, I haven't looked at the result. I can find it if you're interested, but probably the intuition is correct, because S terms don't destroy information. So it always grows. And so you can, at some point, you know that it can never stop, but it will just keep growing.
Okay. Well, it's not confluent. We don't actually know. In the infinite case is probably less clearly understood.
Sorry, right, yeah, the SK combinators may be confluent in cases where you effectively don't have conditionals. That I would have to look into. I know that if you just have SK combinators and a conditional, then it's definitely not confluent.
I thought that they were confluent, actually. That's my recollection.
Yeah, I mean, it would make sense given that you can translate lambda terms into combinators. But there are certainly cases, I mean, well, there's a big paper called Combinatory Reduction Systems that I looked at just before this meeting that has a bunch of these confluence results. And there are certainly variants of combinatory logic that don't have confluence. Whether the SK combinators without conditionals have confluence or not, I don't actually know.
Right. Okay.
I mean, there's an explicit example here of a non-confluent combinatory logic system.
Hold on.
Which they then modify so as to be confluent.
Okay, so this is an example of one where this is the SK combinators.
So then, the system shown just below the SK combinators is known to be non-confluent.
I see. So there is something that can be represented in terms of combinators although it's not clear what T and F are here.
I assume they stand for true and false.
Right.
I see. So they're fixed terms.
Yes.
See, that is not a type. Well, yeah. All right. So okay, Roman, do you know whether the SK combinators are confluent?
Ooh, no, I don't remember enough of it, but I would think they are not, because I mean, in the simplest case, you can have one chain that doesn't terminate and another chain that does terminate. So
Let me show you
they
something.
cannot be confluent.
We just recently got. This is from 1927. Did I show you this yet? This is fun. This is notes by Haskell Curry, in which Haskell Curry has more or less independently discovered combinators, and then he found the paper by Schoenfinkel. And the most remarkable thing about these notes is the use of an @ sign for function application. Don't you think that's cute? I mean, it's this exact same thing that we're doing.
But was that @ sign already? I thought that was younger, but
Which, the @ sign?
the @ sign.
Well,
yes.
the @ sign existed in 1927.
Oh.
I know.
Okay.
I mean, the @ sign did not come with ASCII keyboards. It used to be the case when I was a kid, at least, that it would be like you would see 5 apples at 3 shillings or something.
Mhm.
I wonder whether his precedence works the same way.
Yeah, must be. From looking at this, I would say it's left associative.
By the way, is Matthew here, and can he speak?
I'm here. Yes.
Oh, okay. So, do you know the answer to this?
Yes, I do. So, first of all combinators are confluent. In fact,
okay.
That's the Church-Wasser property.
Okay, Matthew, speak up. Okay.
All
right.
So all.
No, I can hear you. I can hear you. I can hear you just fine. I said I was meaning that in general. We've been talking about this, and you already knew the answer. So, okay,
right.
Tell us what.
There's actually more to say. You are also getting termination confused with confluence. So you can have these combinator expressions. Well, they'll terminate for some evaluation order, but they don't always terminate for all evaluation orders.
That's what I thought was the case.
Right. Yeah. That's what happens if you have one that's defined recursively. So there'll be one evaluation order where it might just keep going and recursing forever, but there'll be another way to like take one branch out.
All right. Can we get straight the first question?
Okay.
Is combinatory logic, it has the Church-Wasser property, yes?
Correct.
Under strong reduction.
What does that mean?
As in not under eta reduction.
Yeah. Well, we don't have to really worry about that. So.
Okay, let's understand this. Confluence of combinators. Okay. What is eta reduction? I don't remember.
It's a variant of beta reduction for combinators.
Okay. So
we're basically only doing beta reduction. Beta reduction is when you do function application. That's really all we're basically doing in this case.
Okay, so can you tell us the result? Okay, first question. If I give you a combinator expression, okay, is it the case that if it terminates, then it will always terminate at the same thing? True or not true?
Correct. That comes from the Church-Wasser property.
Okay. So the claim is Church-Wasser implies that if the combinator terminates, if the combinator reduction terminates, it always terminates at the same result.
That the termination is unique. There's a unique normal form is the terminology that's usually used.
Fine. It always terminates at a unique normal form. Okay. But any given scheme for evaluating the combinator may or may not terminate, correct?
Correct. There is one scheme that's known to always terminate if it does terminate. I believe that's leftmost, outermost.
Leftmost, outermost, yes.
Right. Or maybe it's outermost, leftmost.
No, it's leftmost, outermost.
Okay.
but that's sort of infinitely lazy.
Yeah.
I mean, yeah, okay. We will discuss that in a minute, leftmost, outermost. And I mean, that was what, when I thought about this before, like 40 years ago, that was what I was trying to emulate, was a parameterization of leftmost, outermost to rightmost, innermost, and so on. Okay, we have somebody on the live stream pointing out that the at was first used in the 16th century. Interesting. Okay, so first point is, if it terminates, it always terminates in a unique normal form. But different evaluation orders may or may not lead to termination, correct?
Correct.
Okay. If it doesn't terminate, it is also the case that there exists a way to get, you'll never get stuck. True statement? That is, if you look at the multi-way system, it will have our causal invariance property. True or not true?
I don't understand the question.
Okay. If I were to look at, if I were to compute a multi-way graph from a combinator, is it the case that the multi-way graph will have the causal invariance property?
My guess would be the answer is yes.
That's what I think too. Okay. So let's try to, okay. So again, our objective here is to understand, okay, so I think what we should do next is try to actually make a multi-way system from combinators, okay? Just so we see what it means to do different evaluation orders on one of these combinator expressions. Because what we're seeing here, like this expression here, gets very big. I'm sure I know that in the NKS book I had worked out what the simplest combinator expressions that get to certain sizes and so on is. Like this one, it says grows to a maximum size of 1263, and then let's try that one. Okay, let's say we go to 100 steps. Okay, so with this evaluation order, notice this thing. So you claim that the fixed point that this eventually ends up with, right? If I just say nest here, that's ending up with a fixed point that is that, right? But somewhere in the middle here, so I'm trying to understand if I can think about this, there are different reductions happening here. And can I think about this as some kind of, what will be the reference frames what is the foliation that corresponds to a certain evaluation order here? That makes sense? Matthew, do you understand what I'm talking about here?
No. Okay. I mean, and of course that's what we're doing. We're trying to find the connection between these two different ideas that they seem like they should be connected, but we're not sure exactly what the connection is.
Yes. Right. I mean, look, evaluate, how would we parameterize? Let's think about it, pure language design. How would we parameterize this evaluation order? So here, /.c rules is just going through, and the first time it can apply one of those rules, well, it's trying to do as many rule applications as possible. Okay, so we could write this differently if we wanted to, by saying, so that this down here, so we say, different orders of rule evaluation, or different evaluation orders. Okay, so this one here, let's just do this. Hold on, let me show you something. So I reckon if I say nest this, I don't know, 20 times or something, I'm going to get some big complicated combinator expression, right? Okay, so if I take that expression, let's call that EEE, is that. I take that combinator expression and I say /.c rules, that's going to do some reduction on that thing, okay? But if I were to take that and I were to say, and I believe that does multiple, okay. Actually, if I say replace list, actually, this is going to make a big mess, I think. If I do this, okay, replace list of that, comma, C rules, why does it do that? I thought replace list, oh, it's only going at the top level. People understand the issue here? So the point is that is applying. So what we really want to do is to say map all of replace list of hash comma C rules. This isn't quite right, but anybody see how to do this better? Oh gosh. See what this is doing? Oh yeah, good point. Do you understand what I'm trying to do here? No.
So you want to look at each node and see.
I want to look at all possible replacements.
Yes,
that
but
can
I
be
mean,
done.
for each node, there is probably only 0 or 1 replacement.
Fine, so let's go figure out in these nodes. Okay, so then what we want to do is a match queue on these nodes, right? So on the node, each node will say match queue to, so let's take C rules, right? And let's turn that into a pattern by just making that a vertical bar.
Steven, can you add the option heads goes to true to map all?
In this one here.
Just in case it's a matter of not applying to heads.
Yeah. Oops, heads goes to true. No. Okay, so then this is the pattern that we are trying to figure out whether it matches. Okay. So that's our pattern. And now what we want to know is, as we recurse through this tree, where, yeah, I think we want to combine position with map at.
Find all positions where this matches, right?
Right, that's what we want to do. So I guess what we just say is position in, let's say, EEE, or let's just start off with the initial thing. Position in there of C pattern. Okay, now let's say, is that really right? That it only matches in one place? Well, let's do it on the EEE thing. I bet this needs a heads. Well, let's try heads arrow true. Okay. Let's try the same thing for that EEE object. Okay, so that's showing us where this pattern could be applied in that object, right? So now the question is, which of these applications do we actually do? So let's take a look at this as as we go through the nest here, as we go through successive levels of nesting. So this is going to tell us for each level of nesting. So we say nest list here, and we'll say, let's say whatever it was, 200 times. And then for each one of those, we go through and do this.
This is exactly what we designed proof object for.
Okay, well then let's use it. But hold on, let's first of all we get this. Okay, so here, so now this is telling us how many possible. Okay, so that's giving us the map of how many possible applications there were at each step, right? Okay, so this is telling us the level of ambiguity at each step, basically. And in the end, it goes down to 0 ambiguity. But okay. Well, Jonathan, so we got a couple of different things we can do here. So what proof tries to do is to find a path to, if we say the fixed point is blah,
yes,
then it should give us an optimal path through here. This is one path. What we got here by doing this nest list is a particular path through a series of reductions.
Right.
Okay, so
and by the way, I'm still not convinced about this whole Church-Rosser thing, in the sense that combinators, as we have defined them above, as effectively pure function, well, as pure functions with no external variable dependencies, those can be symmetric. You can have symmetric reduction rules, which means that they're not equivalent to lambda calculus, they're equivalent to symmetric lambda calculus, which doesn't have the Church-Rosser property. And
What is symmetric lambda calculus?
Well, lambda calculus where beta reduction can be symmetric.
What do you mean by symmetric?
So you can transform in both directions.
Okay.
Which is something we allow with the definition that you gave above, I think.
Okay, let's put that on the side, and we need to answer that. But let's understand this for a second. So,
okay, I mean, yeah, so symmetric. Once you allow symmetric reductions, it's definitely not confluent because you can simulate equational logic. And
no, I would actually disagree with you. So I think when you say symmetric reductions, you actually mean what's called a conversion. Conversion means you don't go the reduction or the reverse reduction, and it doesn't really matter. It still obeys Church-Rosser.
Really?
Yes.
Okay, there are a lot of incorrect papers then. Okay,
but so Jonathan is putting papers in a chat here that claim other things. So let's take a look at these papers then.
Well, I mean, here's the symmetric lambda. Well, that's the symmetric combinator case. Here's the symmetric lambda case. They both make claims of non-Church-Rosser, which would make sense because I think, well, if it were the case,
which one is the combinator case? The first one you sent?
The Project Euclid one. So no symmetric combinatory logic that contains at least two symmetric combinators has the Church-Rosser property. Which would make sense because otherwise, if it were the case that you could construct symmetric reductions and still have a confluent term rewriting system, then this would mean you could do equational theorem proving without the need for completion, which would be amazing.
Equational theorem proving in what? In combinatory logic?
Yeah.
So you're saying that if there is confluence, then you don't need completions. Then you should be able to do just a one-shot version of. I don't know if that's true because of efficiency of. I mean, it might be the case that you need completions to essentially store lemmas that otherwise you'd have to recurse back on.
But you don't need to do completion to do that. To store substitution lemmas, you don't need to do completion.
All right, let's look at this a little bit more experimentally. Okay. So first point is, okay, so parse through the network of possible reductions. Okay, we've got two known ways that we can do that, right? Way number one is the slash dot or slash dot approach, right? That's one known way to go through that network. Okay, so slash dot is one of them. Another way is essentially find equational proof, right? That will be another way to get through the network of possible reductions, correct? Do we have any other ones? Is there one with graphs?
What does slash dot actually do? From the inside or from the outside? Or?
It starts from the beginning of the expression. It recurses the expression tree, and it uses, I believe that, I don't know what it does in these deeply nested trees. If it was what it normally does is it will go and back up the recursion, and then it will try running each rule at each level in the recursion. Did that make any sense? So my claim is that if I do this, if I say f of a, b, b, slash dot, a goes to x, b goes to y, it could be the case, right? It does that. Okay, now if I do this, if I say a of a here, I was not expecting that. Why does it do that? Why does it do that? It tries to do the maximal reduction. I know it tries to do the maximal reduction without recursing. Do you get what I'm saying? Oh, I know what happened. I know what happened here. If I were to change this into, if I were to have something less trivial here, if I were to have a of x blank goes to, a x of x. Okay, then I believe it will only do it one level here.
You could also just change that b goes to a. I think that will also illustrate the difference.
Oh, okay. So you're saying, okay, so in this case here, that didn't do the inner recursion, but it did come back out. If I were to have this as A of U here, it comes back out and does that one. Did you get what I'm saying?
So is it outermost?
No, I don't. Well, yes, I think it's outermost, but I don't think it's pure leftmost, right? Because what it's doing is it's doing multiple pieces here. Okay, Jonathan, what were you saying here? You were saying
So
in this
if you
case,
take your example and you change that to B goes to A, that will illustrate the difference, right? Because the point is slash dot is not iterating until a fixed point, whereas slash slash dot is.
Well, I think this was a different issue. I mean, so B goes to A here. Okay, if I were to now do slash dot here, this would just recurse forever.
No.
Oh, yeah,
A gets converted to X.
Yeah, right.
So it recurses to a fixed point.
Right.
That's the point.
Yeah, but it tries to get to a fixed point using a certain evaluation order. And that evaluation order may or may not. So let's give an example where there is an evaluation order where it would get to a fixed point, but slash dot doesn't find it. Okay, so I'm pretty sure a bunch of these combinator things have that property, that there is a way to get to a fixed point, but slash dot doesn't get there. Does that make sense?
Well, but if it is outermost, then it would find the fixed point.
That's in the theory that's okay. It doesn't. Okay, in practice, it's more complicated for reasons that the original definition of leftmost outermost had to do with the evaluation of recursive functions, at least as of when I last looked at this, which was basically 1980. It had to do with a specific model of evaluating recursive functions, and by the time you have these more structural symbolic expressions, it wasn't clear that applied. Okay. So I think it's more, look, can we try to make the multi-way system from combinators? Is that, I mean, there are two things we could try to do. I think that's the most useful thing to try to do, is to make the multi-way system for combinators. And then, I mean, the thing I really want to get to is how do we parameterize this? Is it clear what the problem is? First question, is it clear what the problem is? The problem is, say it again, slash dot has a particular, essentially, recursion order, right? Colon equals has another recursion order. Does that make sense?
Yep.
And the question is, can we parameterize that recursion order in some meaningful way? In particular, yes. Can we use, so Jonathan says yes, as in he understands the question or he has a way to do it?
Well, that's what proof object does, as I said.
Is what?
Is parameterizes evaluation fronts.
How?
Through replacement operations and part specifications. If you look at
I mean, what it says, right? Let's go look at that. But I mean, what it's doing is it's saying what it did, right? What I'm saying is to be able to say in advance what you want to have happen, because proof object is an after action report, so to speak. In other words, these things worked in getting the proof object.
Right. But you can't specify reference frames in a causal graph for a non-causal invariant system a priori, because the different reference frame choices will lead to different outcomes. So that they will constrain what reference frames you can pick in future.
Sure.
So for a non-causal invariant system, that's the best you can do, is an after the fact report.
Well, not necessarily, because what you try, okay, let me understand what the analogy is between this and like Grosvenor basis orderings. Okay, so we've got yet more issues here. Okay, so another one here is Grosvenor basis orders, which I've never understood.
Well, they're the same as Knuth-Bendix orders. The Grosvenor basis reduction order is the same as the Knuth-Bendix reduction order, but for a finitely presented monoid.
All right, well, let's understand that.
Steven, I sent you a few minutes ago a notebook with a connection of combinators and find equational proof.
Okay. So what is this? This is.
So we had seen this before. So we have the rules for combinator actions at the beginning in the language that find equational proof will understand. And then there are a couple of examples of proofs. of results given in the Wikipedia page.
Okay, so hold on, let me just save this in the right place here. That is definitely not the right place. Hold on. Sorry, just a second. Just go ahead and save it there. Okay. Okay, so now what is this? So this is saying, this is the axioms for combinators here.
Right, so we are using left T for this combinator apply operator that Roman wants to have.
Yep.
And then just go to theorem 1 or theorem 2.
Okay, so this is saying, this is, so let me write that out in a different form, okay? So, how do I translate your thing with left T into my version with just a function application?
Well, left T is add.
Okay, so you're saying this thing here, an at is the same as construct, is that true?
Exactly, yeah, change left T by construct. You need a dot?
Oh, yes, thank you. Okay, all right. And let's just also change s goes to lowercase s. K goes to lowercase k. Okay, all right, so that's that. And so now we do that thing slash dot C rules slash dot. Okay, so that's X. So that's what that reduction gives. So this is now saying you can find that reduction by an equational proof. And here's the proof object. Okay, so let's do that then.
Right, so I think what Jonathan was saying is that the proof object will now report in which order these things were done.
Right, so those combinator axioms, okay. So now we say in here, here's our theorem. So this is now the proof object. And so now we get out, so we'd say that, what do we want to say? Proof data set, right?
Right.
Okay, so now Jonathan's statement about where it did its thing.
Yeah, if you look at the inside of a substitution lemma, for instance.
Where is it showing?
In this particular case, it applied at position 1, which is not super exciting.
Okay, well, let's try the next case then. Let's try the next case, which is more complicated.
Right. But my point is just that the substitution lemma, the design of the individual proof of a substitution lemma is a parameterization of an evaluation order.
Yes. I mean, although we've never really liked it very much. I mean, these part numbers are kind of a grotesque way to do that. Do you agree? Or, I mean, okay, so let's try taking this. Okay, so there, I see. So those positions there are the positions in the currently achieved state of the universe, so to speak, saying where the rule will get applied next. Correct?
Sure.
Yeah.
So this is essentially one branch of a multi-way system that successfully gets to the fixed point.
Right.
And your claim is that not all branches of the multi-way system will act similarly, and Matthew's claim is that they will. So we're
well, if you restrict yourself to S and K combinators, then yes, they will. But if you allow for symmetric combinator reduction, then I'm pretty sure they won't.
Okay, I still haven't understood what symmetric combinator reduction is. What is it?
Symmetric combinator. I don't think it's something we need to consider. So the definition here that I'm taking out of a paper is that a symmetric combinator, symmetric lambda calculus combinators are considered to be part of lambda calculus. Symmetric lambda calculus is lambda calculus where expressions and expressions and continuations are treated in a symmetric manner. So just as the way that you might abstract over expressions to receive an argument of an expression, the article says we can abstract over continuations in symmetric lambda calculus to capture the current continuation. This is something from theoretical computer science that I think is not necessarily relevant to what we're doing. I think we're just doing classic lambda calculus. We're not doing the symmetric lambda calculus.
Okay, so we're not sure, but that's okay. Let's work on that hypothesis. Okay, so we have one example here of where you can see, okay. So can we try to actually get the multi-way system? Okay, now we're depending on okay, so we need the this is Jonathan's story because he's the one who knows multi-way system because he wrote most of it. Let's pull up multi-way system. Let's see. Okay, so this is documentation for multi-way system. Okay, so the challenge here is to define using these things, right? The state of evolution function, state equivalence function, etc., to define combinator reduction. Yeah.
Mm-hmm. Right, which is fairly easy once we agree upon a design. Okay,
but so let's take as our minimal design, okay, which is not going to be the final design, right? Minimal design, we're just talking about, S of K of whatever, okay? I think we should do that should we do that rather than left T design? Comments from people? I mean, just for the sake of generating something that we can look at. Let's do this instead of the left T design, right? So this type of thing will be the form of a combinator expression. Okay. Okay, so now the question is we need to write down these, this thing. By the way, if you were claiming right before this meeting that Turing machine was a supported type. It's not listed here. Is it in fact a supported type?
Who was claiming this?
You were.
When?
When you were talking about non-deterministic Turing machines and the fact that I had messed up my understanding of them. You were saying that multi-way system supports Turing machines.
No, I was saying that well, any computation performed by multi-way system can be viewed as a Turing machine computation, and depending on the event selection function, it changes the type. Okay,
but we don't specifically have non-deterministic Turing machines supported yet.
No.
Okay, fine. I think I had one example of one of those. Okay, so, okay, so can we just work out what, for this representation of combinators, right? Probably not our final one. Let's try to work out what these things are to get a multi-way system for combinators. So the goal is to draw the multi-way system. This is probably an ambitious one to draw it for, but to draw the multi-way system for one of these combinator reductions. Make sense? So where do we start here? We want a state evolution function, right?
Right, which will be a replace list of the of whatever the reduction term is.
Is it just a replace list? Because the replace list is only going to go at the top level. You see what I'm saying? So I mean, let's start off. A state evolution function is something which has got to take this, for example, and it's got to apply C rules in all possible places, correct?
Yes.
Once in all possible places. So I think what we want to do there is we want to say, we want to do a replace, if I'm not mistaken, with C rules, and we want to then map that. What do we want to do? We want to take all possible positions here in this thing, and we want to do the replacements from all possible positions. Is that right? So we want to say, how do we find possible positions here? I mean, clearly we can just say position of
What's wrong with using replace list here?
because replace list doesn't go multiple levels, I don't think. Maybe it has an option to do that. No, you see, it gives it most end results. Attempts to transform the entire expression.
Oh, okay, yeah, I see what you mean. And there's no level spec.
That's correct. Because what would it return? That's the problem. Replace list normally, I mean, if I say replace list of you know, A of X, B of X, you know, well, actually, let me, I mean, in other words, replace list can only take the whole expression because it has no way to stuff back into a tree where it replaced one part of the tree. Get what I'm saying?
Right. Yeah, I see.
Okay, so
That's
then
the trivalent network symmetry story.
what? Oh yes, yes, it is.
It's the same issue. You can't plumb back in a substructure once you've replaced it.
Yeah, I mean, because the representation of the substructure is different. The representation of the list of substructures is different from the representation of the substructure itself.
Right.
But okay. Okay, so what we're trying to do here, what are we actually trying to return? We're trying to return a list of expressions where a single replacement was done somewhere in that expression, right?
Right.
So what, I mean, just to be clear on what would happen, if I say map all of F onto this expression with heads goes to true, then I claim that will map F's in all possible places, but that's not what I want. What I want to do is I want to have an expression where I have a list of expressions where F has been put on all possible parts. See what I'm saying?
So you want to find all sub-expressions, right?
That's correct. And somebody has, SWSH has put on the live stream a suggestion for how to do this. Replace at. All right, well, let's see whether this works. Okay, so this is just saying, I see. So this is a good idea. This is just saying find with position. Oh my gosh. Okay, there we go. Okay, so let's just write this then. Okay, so let's call this Combinator cases of an expression. Is what we get by saying position. Let's find our definition of Combinator of C pattern. Let's see rules, which we're going to need. And down here, wherever it was. Okay, so position in expa. And I don't know whether we need heads to true. Do we? Does anybody know?
I think position has it by default.
Okay. All right. So that's going to give us, okay, so Combinator cases will tell us where we could in principle apply one of those rules, right? So Combinator cases of this says there's only one case. Let's pick up a more realistic example of this, preferably not something that grotesque. Let's just do this. So here, let's just do that like 3 times. Okay, so now we've got an expression there, and now we'll say Combinator cases of that expression. And oh, come on. Is that right? How can that be right? Oh, no. That we forgot an important thing. Comma infinity here. Am I totally confused? Position, we want to know the position level spec. Well, do we need a heads goes to all?
I think both things are default.
They are, yeah, they are actually. Okay, so what is going wrong here? So why is this not finding? Because we know that we can apply C rules to this.
Yes, at the outermost.
Well, the outermost level, we've got that. But the claim is there is no more inner application. All right, well, let's
Which
try
looks
another.
correct.
All right, okay, well, let's try a different one of these. Okay, maybe we just were unlucky with our sample. What's going on? That can't possibly be right, because look, C rules take this expression and apply C rules to it. Oh, I have a much more horrifying idea. Did it not do anything? I don't understand. Did it really not do anything to that? How can this then work?
It did something, but it didn't do very much.
Well, okay, yeah, I can see it did something there. Well, the fact that it didn't do very much is its prerogative. But it certainly did something more than nothing, which is what this is reporting here. Let me see whether there's something. Am I confused? Is this a problem? Could this be a problem? Okay, I am very confused. Why didn't this work? So down here, why is this not reporting any position that matches either of these? Well, so first of all, is there a position that matches one of those? So S, O. Okay, so that clearly matches, right? That there clearly no, it doesn't match the S pattern. Okay, how does slash dot manage to do something here when this doesn't? Yeah, let's try zero infinity. That's a good suggestion. What's going on? Okay, let's see what slash dot actually did. Oh boy, we need some kind of diff of these two expressions. What this did is it moved the K somehow inside there, right?
Yeah, so there must be an S where probably it applied it to the whole expression. Yeah. So I think it has.
No, that S. Oh, that I see. That S is that's the first argument of the S.
Then the second and K is the third.
There's the second argument and the third argument of the S.
Yes. So
okay.
It's at the outermost level, and I think the problem is that with this position thing.
Why is the position not finding that?
I don't know, but
well, if you do position, x comma x, it returns the same thing. So I think it just doesn't find, if it's the whole expression, it returns an empty list.
But why is the zero level? Oh, because it's the part specification. This is a list of one element. We are just totally confused. It's a list of one element that is the part specification of what you have. See what I'm saying?
Right.
Okay, so I claim that this is going to be more civilized if we do this. If we look at this with nest list, let's say 8 here, and then on that we say combinator cases. Okay, much more civilized. Okay, so those are the possible applications of this. We have a suggestion here about how to visualize these functions, which would certainly be useful. Okay, so here we've got that, right? So this is showing us where in the expression. So in particular, we could do the following thing, okay? Potential idea here. This may be very, very obscure. So let's say we say map at of an expression. Okay, so combinator framed of a combinator expression. I'm suggesting that we say map at of the combinator expression with I'm sorry, map at framed onto the combinator expression with combinator cases of the expression. Okay, so what that should do, if it's right, is if we could say here, we could say, for example, combinator framed okay, so that's showing where the applications of combinators happen in those expressions. Make sense? Or where they can happen. So now our...
I mean, I would think that notation with an application operator would be a lot more readable, but I think that framed is a big improvement.
Okay, well, so let's look. Let's do a slightly bigger case. Let's say 15 or something here. And I'm probably going to have to show smaller font. Okay, so that is starting to show us the tree of where things can be applied. So this is effectively going to show us, this is a piece of essentially the multi-way graph of where things can get applied. So our problem from an evaluation order thing is to select of the possible places where you could hit next, so to speak, here, which ones should you actually do in a particular foliation? Is this making sense? So what we did here was we picked a particular sequence of reductions for that expression. And then in each one of these, we're saying, where could we go next? In fact, we go to a definite place next. But this is saying, where could we go next, right? And so the problem of essentially foliating this evaluation front is to say, where do we choose to go next? Is this making sense to people? And what we're looking for is a parameterization of where to go next. So, I mean, let's try to draw the multi-way graph from this. So I think we now have. So Jonathan, we're trying to write down the state evolution function for this, right?
Right. So it's a map out of replace of combinator cases.
I think so.
And then you actually, other than that, in the state equivalence function, if you only want to draw the multi-way evolution graph, that's all you need. Everything else can just be null.
Okay, fine. So map out of replace part. No, that isn't quite right. No, it's replace.
I think it's map out of replace.
Oh, I see. Okay, map out replace onto hash of combinator cases of hash. Do you agree?
Seems plausible.
Should we try it in some particular case? Let's try applying that to this expression here, because we can see what that did at the beginning. Not promising. Okay, so the replace. Oh, no, we have to say C rules here. And that's not right either. Because we don't want that. We want a list, don't we, of the results. See what I'm saying?
Right. So you need to map over combinator cases.
I think so. Right. So what we want is a I don't think we can do that with a single thing. I think we probably could do it with currying in some way. Function of that at this, is that right? Great. Oh. Okay, what went wrong here? Okay, combinator cases of E is combinator cases of that thing. Agreed? Oh, that's crazy. There we go. Much better. Okay, so this then is function of E there. So that should be that. Okay, we've got our state evolution function. Now what do we need?
Now you need a state equivalence function, and then everything else can be null, with the exception
so
of the system
state
type.
equivalence function is just same queue. Is that correct?
I think so.
Okay.
You do have to set the other elements of the association, but they can just be null.
What are they?
If you bring up the documentation for multi-way system, we can see.
State event function. So we have to put all of these in.
Unfortunately, so yeah.
Is there a good place in the documentation where I can pull those all out?
Yeah, in scope there is an example, I believe. Wait, no, it'll be in system types, if it's where I think it is. Let me just check that it is actually there.
Oh, here we go. Here's one.
Yeah, it's there.
Okay, so actually here, why don't we just put it
just replace it with that. And everything else is the same.
Okay, so now here, instead of that, we will have, drum roll, this thing here. If this works, I'll be amazed. So far, I'm amazed. All right, so now let's make a states graph of this.
Which will look awful, by the way, because we don't have a rendering function. Maybe do states graph structure.
Odd. Exceptionally odd. That's saying there's no branching here, which seems extremely implausible.
Well, combinator cases only returned one element.
I understand that, but we just had an example up here. This is a nest list on this. You see what I'm saying? I don't understand how it did that. If this is correct, right? So here, right, this is returning. So this shows that there are non-trivial. This is claiming that there's only one way to do this reduction, right? Which seems extremely implausible to me, because we already know there are multiple places we can do the update.
Right, but this is saying that that in that case, same queue returns true.
On all of those updates.
If we believe the evolution function, then yes.
I don't think it's correct. Because look,
let's see a vertex list of that.
What's that?
Let's see a vertex list, or just look at the all states list.
Okay, let's take this thing here, and then let's say vertex list of that. Okay, and let's compare those with what we get by actually doing the explicit. Okay, we want the explicit evolution, which is this one here, right? They're the same. Well, they seem to be the same. Okay, yeah, so this is saying that there's just this is completely incomprehensible to me. But this has a single path of evolution.
Can we not take one of? We had examples above where combinator cases returned something that wasn't a singleton.
Here, it's full of things that aren't singletons. Look at all these things here. Each one of those boxes is a return from combinator cases. See? And then this common thing, each section here, right? This whole thing here is full of multiple results from combinator cases.
Okay, but just for my own sanity, can we try maybe the one that's, there are examples up there of like 1, 0, 1, 1, 1, 1 and things. Can we try whatever expression it was that corresponded to those?
Yeah, it's the same thing. It's the same thing. We're just doing the same thing over and over again. It's this one here. But we can do it. I mean, we can do this here. That was the first 8 cases of this, right? So, okay, let's look at this. Okay, so let's say the first 5 cases of this. All right, let's go a bit further. Let's first 8 cases. Well, how many? Okay, first 8 cases. Now let's say length slash at that. Okay, so the first few are all.
Yeah, so maybe run the multi-way system for more steps.
I did. Oh, I see. Oh, I know what the problem is.
It's only applying one update at a time.
It's only doing one update at a time.
Yeah.
But how did it manage to stop? All right, let's live dangerously, but I don't think this can possibly. I don't understand. This stopped as if it was a fixed point here. In other words, combinator cases, what this is basically saying is that combinator cases applied to that. Oh. That's a single result that says apply it to everything, right? That's the.
Yeah, that's the last one, right? The last one above is the empty list.
Here.
Yes.
So should we modify the evolution function to deal with that case?
Yes, but how do we need to do that? I mean, so if it's a null list, what is it supposed to do?
It should just do replace.
So your claim is that this map at here, in the case where the hash sign is, why doesn't map at do that correctly? Let's just see what map at does in this case. Okay, so we're saying map at of f onto, let's say, 1, 2, 3, with the position for map at being, it does the right thing. Why didn't it do the right thing then?
So what happens if you apply C rules to that, just to the whole expression there? Is it a fixed point?
Okay, so we say replace. I can't even tell.
No, that's different. There are 2 Ks for one thing.
Oh yeah, right.
But is mapat finding list of empty list or just the empty list?
You are correct. The problem is that the problem is that this map here is doing the wrong thing. So we have to say then, well, I mean, the hack version of this would be if somebody is pointing out here, map at is suggesting map out of replace C rules. Oh, I see. You're claiming that we could do this. I don't know if that's correct, but we can try. Oh, no.
Don't do 100 steps.
Da-da-da-da.
Nice.
Thank you. Okay. Oh, very interesting. All right. So this now, okay. So first thing, this looks awfully causal invariant to me. Look at all those mergers. We can even test causal invariance for this, can't we?
Yes. Yeah.
Why not? You don't trust your causal invariance checker?
Well, no. It's S and K combinators. We know that.
Look at that creature. What the heck is going on there? That is a Combinator explosion if I ever saw one. All right. So what we are trying to do is to figure out in that mess. Well, now we can work out. Oh, we can work out the multi-way causal graph from this.
No, we can't.
Why not? Because we didn't give event selection functions.
We need a lot more information.
Okay. All right, but
which actually is not too hard to write. Now, I mean, if we agree that this is the design, I can easily put that together.
Well, I don't think it is the final design. I think there's just there's just an exploratory design.
Okay.
Let's try one of these things that eventually turns into a fixed point. This S, the thing with pure S's that turns into a fixed point. Let's see, the largest fixed point, case D. Where the heck is case D? Growl, I need to know. So these are cases that grow exponentially. So let's try this one. Clicking on a Combinator expression that has, let's just try 5 cases here. So it's interesting that it takes a while for these things to start. What? This is really weird. I've never seen a thing that does this, where it takes so long to kind of get started. Oh no. Well, we know it grows like, wow, it's really weird. Not what we've seen in other places where it's sort of, help. No, don't crash. Come on. How big is this? We have no idea. Formatting notebook contents. Let's see what's going to happen. This, great. Well, I'm just going to try. No, this thing is absolutely huge. Whatever it is absolutely monumentally huge. By the way, do you know what color scheme it's using for this multi-way system? Is it using it some kind of default for the
Yeah, it's using the standard state node coloring scheme, the one that Jeremy designed.
Okay.
I mean, it wasn't optimized for this number of states, so it looks a bit weird with the gray arrows.
This notebook is like, this must be like absolutely monumentally huge. Okay, let's see. We got to 15 there, and it was starting to do things. I'm just going to go to 17 because that's about as far as I think I can go. So actually, maybe we can get to 18. All right, so reminder of what's going on here. So this is showing, this is the thing that we need to foliate to be able to understand the evaluation order for combinators, right?
We're not foliating. We are defining a path, which we can now do, incidentally. I mean, we
okay.
If you say...
define a path to do the recursive evaluation, but what I was trying to do was to give essentially something which says, which is a sort of a general definition of what order to do these things in. You're right that it's not. We're not trying to get equivalence classes,
right? Which you could do in the multi-way causal graph, but that's a more complicated case and requires notions of space-like separation.
One thing that so the reason if we were trying to evaluate the Combinator expression in parallel, then we would care about that, right? Because what this is saying is there are pieces of this that are not causal dependent. Right? There are pieces that could be done in parallel, right? So there's a question of what can we parallelize here. So the foliation question, foliation is equivalent to sort of do you agree? People agree here? What can we parallelize?
Sure.
What is the dependency graph here? But okay, but even picking a path. Okay, so let's take this thing here, line 18. Let's say layered graph plot. Well, let's just see what happens if we say I don't know what it's going to do. Graph 3D of 118. I don't know whether that's going to be very interesting. It's rather botanical. I can just imagine picking one of those blueberries, but not very useful.
But the point is, once we have event function specified, then the that association allows you to specify an event selection function, which is what we're talking about.
Indeed, which will give us a path. Right. But what criteria could we use for the event selection function? Okay, so this is quite interesting. So that's the layering. That's essentially layering by evaluation, by recursion level, I think. I think that's right. That shows us in the sort of cosmological rest frame, in effect, the sequence of things where the number of events that took place. This is saying at each level here, there's a different number of events that took place, different number of rewrite events that took place. I don't know quite. So the question that we're asking ourselves is, if we want a path through this, let's find one that goes to a fixed point but takes a while, okay? Because I think that's what's going to be the most. Let's take a look. Which one did we have here that went to a fixed point? What was the one that we had up here? This one here. Do we want to live that dangerously? We might be able to do that one. Let's try this one here. Okay, so that's this thing here. And so that one, what we should see, this may be hopeless. We may have to take a simpler case.
Fixed points are going to be hard to spot in the multi-way evolution graph because they're statements about a single path.
No, they're not. It goes to a normal form. The multi-way evolution.
Going to a normal form is a statement about a single path.
No, but in this picture, because of the state equivalence function, every single thing is just going to go back to a single dot here.
But you can have the thing can be confluent and not uniformly confluent. This is the point I was trying to make earlier. I mean,
all right, well, let's see that.
You can have a confluent system where evolution branches can be infinite, but you can still have some evolution branches where there's a normal form.
Okay, well, that's this question. Okay, great. Okay, we're going to see, as usual, the experiments clarify what's going on. So it could be that both you and Matthew are correct, that every finite branch terminates in the same thing, but there exist infinite branches that don't terminate at all.
Yes, I actually agree with that. I had actually said that before. We are not in disagreement about that point.
Okay, so let's look at this thing. Okay, let's look at this and let's see what it actually does. Okay, so let's say, let's define this as Combinator multi-way graph of xbar and t. I think those are the only parameters, right? Okay, so let's say Combinator great. Okay, now it's starting to blow up. Okay, I think we're going to have to try and find one of these experimentally that isn't this. Is that the same expression? No, it's a completely different expression. So that was S's. This has that same kind of structure, which is kind of interesting. Okay, so let's try 14. Oh no. Okay, that's already getting really complicated. So I think we're going to have to do this. Okay, who knows how to get how to generate all possible S combinator expressions? Can we do it with groupings? I think we can do it with groupings and construct. Can we not? Jose, anybody else?
Well, unary things are not very good for groupings.
Okay, so but this isn't a unary thing, is it? Isn't it a tree? Oh, what the heck is it? This is the total number of combinator expressions is blah. So I love the way that I just say that. I wonder how I got that. Or in general, 2 to the n binomial of this. See page 897. Let's try that.
The combinator expressions are just binary trees where you replace the leaves with either S or T. S or K, excuse me.
Okay, so so how do we get binary trees? We can get binary trees from groupings, can't we?
Oh, yes, sorry, I was confused. So yeah, it's grouping of, it will be list S and K, construct goes to 2. And well, we need to put S's and K's many times in the first list.
Okay, fine. Let's just do S expressions to begin with. Okay, so let's make a table of, let's say, 5 S's. Okay, so those are all the S expressions that we can get with 5 S's, right? So for each of those, I'm going to live very dangerously, and I'm going to compute the combinator, because since actually I know that they all terminate, because I remember that. So let's say 10 steps, and let's map that over this collection of the S combinator expressions. Thrilling. Okay. All right, so let's try going to the next one up. Mega thrilling. Well, actually, do we know that we've got enough steps? Let's see, if we go 20 steps here. Still the same thing. Okay, let's try one more time. And let's say graph that image size tiny. 7 of these. Okay, let's see what happens. This is taking forever. But we're trying to find the first example where, but we could actually just compute. I wonder whether any of these get huge. Let's compute which of these doesn't lead to a trivial fixed point. Arg. All right, let's do this. Let's just say nest list of hash / dot c rules. No, / dot c rules on hash of, let's say, I don't know, 10 steps. And then let's just say length. No, leaf count / at that. I should really be using better functional constructs here. And then I use this groupings thing, and this should give me the, okay, there we go. So that's showing what happens to each of those. So they mostly go to fixed points here. Okay, there's one that's doing something more non-trivial. So should we pick up, let's pick up one of these that, well, let's see if they actually go to a fixed point. So let's say 15 steps. Okay, so there's some that seem to be growing without bound here, so far as we can tell. Okay, let's take this one here that like goes to a fixed point, but it takes a few steps to do it. Makes sense? And let's, for the sake of knowing what the heck is going on, let's do a hash goes to that. Okay, so this one here is one that goes to a fixed point, but takes a little while. Makes sense? So let's try that. Oh, okay. All right. This is going to be more interesting. So let's say we live Okay, that's an interesting object. Quite an amusing object.
Looks like the N1 moon rocket.
Well, look at that, though. Look at that. That didn't change. So what that's saying is, let's do a layered version of this. Okay, that's
But wait, there are cycles.
Well, isn't that interesting? Closed time-like curves.
So it's definitely not causal invariant.
Well, in some weird sense. Okay, so hold on. Let's just get the layered version of this. Okay, now notice in the layered version, notice that everybody is going there. And I don't see any cycles.
Yeah, okay. That may have just been an illusion.
So there appears to be a fixed point. Let's keep going for longer. Yeah, it's a fixed point. Okay. So this is saying, so this is an example of a combinator expression. Okay, so this is a great example of where we can ask about the evaluation. So any particular evaluation order is a path through this graph, right? And the parallelization here is those nodes of this graph that can be independently computed, correct? But only combine later. All right? Agree, disagree?
I disagree, but I don't know if anyone else does.
Well, explain why.
Well, because the parallelization is a question of multi-way causal connection, not multi-way evolution connection.
That's true. You're right. You're right. So what we need to do then is to show on this also the causal graph.
Right.
So how would we compute the causal? We need to then, okay, but this is a nice example because this is a nice example. So far, there's no evidence from this. Okay, let's just compute a few of these other ones, okay? Pick another one that you'd like here. I mean, these all, okay, let's try this one here, which might not terminate. Okay.
It doesn't look promising.
Well, I agree, but actually there's two different cases here. There's this one here as well. All right, let's try this one. And let's not be that dangerous. Great. That looks very non-terminating, but let's take a look. Okay. Wow, these things grow quickly.
Now, can you identify identical sub-expressions?
We did that. This is a states graph. This is, I believe, this has already
part of that on the left is just another copy of the whole thing, right?
I don't think so. I think it's a copy of the whole thing with potentially with an S wrapped around it or something like this. It should be the case that every node here is a different expression.
Or any pair of nodes where same Q returns true will be merged.
But same Q, these things are same queued things. There's no way to have expressions that are different. See what I'm saying? I mean,
we could do that. You could set include step number and include state ID if you wanted to not have that equivalence.
Why would we want that?
I don't know, just to illustrate the difference. But I agree, it's not useful.
But let's see if we can generate the causal graph. I mean, okay, so what are we learning from this? We're learning here, we've got a nice, presumably causal invariant thing that goes to a normal form, right? In this case, we've got something that you're claiming isn't causal invariant. Well, it doesn't go to a normal form. That's fairly likely, at least from this picture. And moreover,
I have no idea whether it's causal invariant or not.
Okay, but the squiggling out of causal invariance by virtue of the fact that, so one question is there a path that gives a fixed point here and another path that doesn't?
Wait, actually, hang on, wait. If you go to the far left there, that's a normal form.
Why do you say that?
Because there are way more reduction steps on the right than there are for the ones on the left. Unless I'm, again, being fooled.
I'm not sure that's correct. I'm not sure that's correct. Let's look here.
3, 4, 5. Maybe not. I don't know.
Well, okay, so the question is, these are layers, right? But the problem is, because of the evaluation order, it's not obvious to me that it did the right, that it has tried applying as many things on this side. So what we will want to do here, comparing these two things, right?
Yeah, hang on, wait, no, yeah, it definitely has reached a normal form, because look, you can see the same cluster of states above and below on the left.
Well,
that cluster hasn't evolved.
Can I interrupt?
Yeah.
Okay, so can I back up for a second and reaffirm that our goal is to find an example where you have one that has a fixed point when you evaluate it some ways, and then goes off and then continually evaluating if you evaluate it in some other way, correct? That's
which is this example, yeah.
Okay. No, so if we're building our combinators only out of S's, this is a special case of what's known as the lambda I calculus. And it's known in that case that if it terminates, there's a specific number of evaluations that will always terminate. Every branch will terminate within that specific number of evaluations. And that's in the lambda I calculus. And if you just use S, that's within the lambda I calculus. So you actually have to use K if you want to get one of these cases.
Matthew, answer the question. Which of these endpoints here? So we can tell which of these is a fixed point, right? By just we could label these. We could let's do the following. Let's say highlight. Let's take this graph, okay, and then up. Okay. So let's take that graph there. Okay.
How many fixed points can there be?
Oh, only one by the church roster.
So these are not fixed points.
As you claim, if the thing has the church roster.
Right.
Okay, so if we take vertex list of this, right, that's going to give us all the things which are, okay, so now we can say fixed point Q, right? And the fixed point Q would be, is it the case that expa, so my fixed point test, and you tell me whether this is right, is expa / dot, no, that's a very dangerous thing to do, / dot C rules. Is that correct? That's my test for whether it reached a fixed point. So what I was going to do here was I was going to say select in vertex Q, fixed point Q. Nothing, nada, none of them are fixed points.
So as I was saying, we need to include K, and I can actually construct the combinator expression you're looking for if you want me to construct it for you.
Sure, tell us what it is.
Okay. First, just as an abbreviation, call the expression S of K, call that I. Say I equals S of K.
Like that.
Correct, just like that. Okay, great. Then let's see. call D, say D equals S of I of I.
Okay.
Okay, and now take the expression K of, and inside K, give it D of D.
Like that?
Correct, just like that.
That
and my
it?
claim is this is the expression you're looking for.
Like the droids. Sorry.
Right.
Okay, so your claim is that this will achieve a fixed point for some it's a lovely looking thing. Okay.
No. I actually misspoke. We have to make a slight change. Let me think for a moment.
By the way, if we want to detect fixed points, I think there's a reasonably easy way to do that.
What's wrong with this way of doing it?
With it, but we can figure out which branches yield fixed points.
Okay.
Because you can compute the vertices that have out degree 0 and then find shortest paths from the origin to that vertex, and then any that have a path length that's less than the number of steps are fixed points.
Oh, okay. The expression we want is actually K of DD.
K of K of D, like that.
No. K is with two curried arguments. The first curried argument is K, the second is D is D.
Okay. All right, so we're saying this thing here. So you're making the claim that this is going to have one place where it gets to a fixed point and the other place where it's going to be going off like crazy.
Yeah, the important point being D of D will keep computing forever. But if you evaluate the outer K, it just evaluates to K.
Okay, so explain what you're seeing in this picture. What are you seeing here? So that appears to be, everything seems to be evolving to this. There's nothing, well, we don't know about that, right? So let's go back, for example, for 7 steps or something and just see what it looks like.
Well, the D of D should keep evaluating forever.
Well, can I color this in some way? Should I color this in some way with the vertices? Should I make the colors of the vertices indicate what's going on? You're saying that there should be things with head K do something different. Is that right?
Oh, well, there's that. Evaluating that outer K is what brings you to your normal form. And if you don't evaluate that, then you can keep evaluating the arguments of that K forever.
Look, there are things here that appear to have stopped, right? And there's another thing down here that appears to be these things here. Let me do my little trick here with the normal forms. I mean, the fixed point Q thing. Okay, so let's take this, and then let's say on the vertex list there, select in that vertex list of that this fixed point Q. Okay, so that says there's just one thing here that is a fixed point. Just K is a fixed point here, and nothing else is.
That's by the Church-Rosser property. It has to be just one.
Well, so okay, so let's find that one. Okay, so let's say K. So in this picture here, we want to say highlight graph of this thing here, comma, and then we just want to say K. Okay, so the K is right down at the bottom there.
I think one problem might be that this infinite evaluation is over several steps and not over one step, because D was just an abbreviation. So it takes several steps until it regenerates.
I really think it'll be instructive if we look at the lengths of the shortest paths.
Okay, length of the shortest path from what to what?
So as I say, we compute all of the vertices without degree 0. So those are all the ones which are either normal forms or which have just been computed on the last step.
All right, so say select this vertex
out degree 0.
Whoops.
Vertex list. Wait, no, hang on.
No, this is completely wrong. We need to get the graph here. We need to compute the graph. Then we need to say vertex out degree in that graph, select a vertex list of GGG, the out degree there, GGG 0. Okay, so those are the vertices without degree 0.
Right, so then if we do a find shortest path from the original state to all of those, we can see whether they're equal to 7 or whether they're less than 7, and we can color them accordingly.
Okay, so find shortest path on this between the original expression, which is this thing here,
and let's just look at length of that to begin with. So there's the fixed point.
Which, the 2?
Yeah.
I don't understand. This is... Oh, look at this picture. I see.
Yeah, we don't know how it's laid out. That's why I'm saying I think you should color it by the shortest path lengths.
From the initial state. But the initial state should be at the top. Why isn't the initial state at the top?
Why would it be at the top?
Because it's a layered graph plot.
Without a specified root vertex.
Well, then let's specify its root vertex. Places the dominant vertex at position. Okay, so let's say that. Okay, so let's do this. Let's say there. The root vertex, let's take this thing here. Okay, explain what the heck is going on. Why are there multiple root vertices, and why is the thing going backwards there? See those arrows going up? I am deeply confused.
Is that what we want to do for Dom? I don't actually know how layered graph plot works.
Well, it says here, places the dominant vertex in the plot at position pos.
Do we have an example of where that works? I mean, if nothing else, we can just highlight the root expression.
All right, let's just highlight it. So in this case, instead of highlighting K there, we want to highlight the root. Okay. What?
Oh,
what
so
the heck is going on there? Yeah, but it's at the top, but look what it's doing. The arrows are going up to it.
Some arrows are going up to it.
Yeah, I mean,
so there's a cycle. Are there cycles?
Yes, SII creates a cycle.
Right. Once you have identity, then you can
D applied to itself, it evaluates after a whole bunch of chains of evaluations. It returns D applied to itself, and it does that indefinitely. D applied to itself evaluates to D applied to itself, evaluates to D applied to itself. So that might be what you're saying.
Okay, so there's a cycle. I mean, that's an example of a cycle.
Right.
So, for example, we could take that, and we could say highlight graph of that, comma, and then the cycle. Great.
Right. And once you have a cycle, then you don't have uniform confluence, and therefore you don't have causal invariance.
Well, that would otherwise be known as a closed time-like curve, yes?
Mm-hmm. Right.
Okay. Okay, so what do we learn from this? So what we're learning is that it is in fact true that when the combinator doesn't terminate, then you may not have causal invariance.
Not necessarily. I think you're seeing loops because what you're doing is you're identifying nodes with specific combinator expressions. Here we have the same combinator expression appearing over and over again. If you instead treat them as different nodes, the separate times that it occurs at, then you won't get loops.
But you still won't have uniform confluence.
Well, we can do the thing you just said, right? If we take the original
state ID, and then but the fact that you still have you have non-uniformity in the path lengths, so you can't have uniform confluence, and therefore you can't have causal invariance.
I don't know what the notion of uniform confluence is about here, but
that you get confluence only makes a statement. Confluence is the statement that every time you get a bifurcation, there exists a rewrite sequence that unifies it. Yes. Uniform confluence is the statement that that sequence can be applied across all multi-way branches.
Fair enough. Okay, but let's take this, and let's take the thing here. Let's I don't know. Let's call it what should we call it? ID'd. Okay, and now this wants to say here. We want to say include. What is it? Include
state ID.
Arrow true.
I think so.
Okay, so then let's take this thing here. And we're living a bit dangerously by saying 7 here, but let's try it anyway. ID'd. Okay, not so bad. Okay, then let's do the layered graph plot of that. Well, then let's do this whole thing here. Why not?
Actually, hang on, wait. You might want to do include state ID and include step number, just to be on the safe side.
Oh, I see.
Nope, didn't make any difference.
What? Well, we don't need the highlight graph here, so we don't care about that. ID'd.
Oh yeah,
I see. But
we don't have the IDs in the.
We don't have we don't have that vertex. Okay, that didn't make any difference. Did it? I think that is the same as.
Yeah, I'm a little bit concerned because there does still seem to be a cycle there, and I'm trying to work out why.
A cycle, even when you include the IDs.
It looks like it, but I can't tell if.
Where do you think there's a cycle? Well, let's
in the non-layered graph plot.
Yeah, I understand.
Let's
just compute whether there's a cycle. Yes, but what's this? So what's that? That's the state ID, right?
Yes. Why are the state IDs the same? Hang on. Oh, yeah. Okay. Yeah. No, I understand. We need to specify the event functions because the way that the state IDs are assembled is that they're from the event IDs, the input and output event IDs, which we haven't specified.
Right. So this is in fact incorrect.
Yep. Right.
But if we can we get the event thing in there? I mean, because that would be a then we could get the causal graph.
When you say the event thing, there are several event functions. The event decomposition function will be non-trivial to write.
Do we need it to get an event? Yes, we do need it to get the causal graph, right?
Right.
What does it need to do?
So it needs to figure out which sub-expressions were created and destroyed by a particular event, which will depend on C rules.
Why isn't it just the position? I mean, which sub-expression was created and destroyed, isn't that just the, every time it does an application, right? With the map at thing, it knows from combinator cases, it knows which ones are going to get destroyed. Combinator cases is the ones that get destroyed.
Mm-hmm.
And the result of this is the ones that get created, correct?
Yes, but effectively you have to do a diff in order to work out because which are going to be created depends on it doesn't just depend on the right-hand side, you also have to sort of mod out by the left-hand side.
Okay.
Even in the strings case, it's not straightforward to write. I mean, it won't be too difficult, but I don't think we can reasonably do it in this meeting.
Fair enough. Okay, but so let's zoom out a little bit what we think we've learned here. Okay. What we haven't learned, because we don't have the causal dependence stuff, is this parallelization. What we also, well, we're still mildly confused. What do we think the conclusion is about the causal invariance question? In other words, is it the case you can get stuck in the multi-way graph and not be able to get back?
You'll always be able to get back. But my point is, okay, maybe phrasing it this way will be more helpful. Uniform confluence is a necessary condition for causal invariance for the following reason. If you don't have uniform confluence, so in other words, you have multi-way branches, which, for instance, extend infinitely, even though there is effective confluence on other branches, you can always make the causal graph arbitrarily different by just following that multi-way branch for another step.
I don't necessarily buy that works infinitely, but yeah, I understand the claim. It's not.
Why wouldn't it work infinitely? I mean, it's even worse in the infinite case, right? If you have a bunch of branches that all terminate at some normal form, but you have one branch that's going off to infinity, then even if the causal graphs that all terminate at a normal, the causal graphs corresponding to the branches that all terminate at a normal form are isomorphic, then the one that's infinite definitely won't be, because each new event you add
I see the claim. I understand
changing the causal graph. So I don't think, unless maybe Matthew has a differing view, I don't think you can have causal invariance if you don't have uniform confluence, and I'm pretty sure I have a proof. But
Matthew,
I don't have an opinion either way.
okay. Matthew has not halted. He's not. It's okay. Well, okay. Let's go back again. Zoom out to again what the original question was. The original question has to do with parameterizing evaluation orders. Okay, which might seem. I mean, I think you guys still haven't understood. I think this is I think if we can really figure this out, this is really useful. Although, we're in the depths of the abstraction of combinators here, but
I don't think this is a problem specific to combinators. I think this
of course it's not a problem specific.
Yeah, this is the general theorem proving problem of how do you specify the evaluation front. How do you specify what the inputs to the lemmas are?
Sure. I mean, look, in theorem proving, the goal is to find a path through a graph like this, through a multi-way graph, that gets you from left-hand side to right-hand side. That's the typical equational theorem proving problem.
Mm-hmm.
And so to say, well, I'm going to favor these paths over those paths, sure, that's a worthwhile thing to do, right? And it's the same problem as the problem of for the Fibonacci evaluation of the recursive function, which thing do you do first there? It's the same problem as depth first, breadth first, parameterizing those. It's all the same problem. I mean, in other words, what we've got, well, okay, to what extent is it the same as finding a total order consistent with a given partial order? I think it's highly related to that. Right? Because, I mean, we're not seeing that exactly here because we don't have a causal graph, but I mean, that at least is a closely related problem. And the problem with that problem is that right now, the formalism we have, what are some reasonable total orders of a given partial order? Right? And that's what we were looking at in those previous pictures. And the answer is there are a large number of possible partial orders, and they're mostly, where was it? Oh, I have to show you that Schoenfinkel note. Here we go. Okay, so in general, right, these are possible total orders of this partial ordering, right? That's a total order of that partial ordering. It's a total mess. We don't care about that one. Question is, how do we parameterize which total orderings we care about? You know, depth first, breadth first, maybe. That's what I think is going to, you know, I think there are primitives to represent these different orderings, and that these will be related to this question about which path do you pick. I mean, I'm looking for, how do we think about this? Because to me, okay, here's a basic question. It's a physics question, okay? This is a Jose Itai, who've been very silent, physics type question, okay? We're parameterizing reference frames. We know what an inertial frame is. You know, it's just a frame that is, you know, progressive slices. What are some other examples of types of frames that we are familiar with?
Accelerated frames, perhaps?
Yeah, and rotating frames.
Okay. So what are the interpretations of those in this context? Because an inertial frame is something where we are effectively, maybe Jonathan already knows the answer, I don't know, to this. I mean, an inertial frame is something where we basically have, you know, this is the cosmological rest frame that we're, you know, we plotted this in sort of the cosmological rest frame. So in that frame, the, you know, motionless inertial frame is just horizontal slices going down. And the, you know, inertial frame at a given velocity is horizontal slices tipped at some angle. What is the accelerating frame?
Well, horizontal slices tipped at a successively increasing angle.
Where you say successively increasing, you mean over time, the angle gets to be larger and larger. Is that right?
That would certainly be one way of representing it, I think.
So in other words, what you're saying is that that means that there is a, I mean, there is a singularity in the accelerating frame if you try to extend it to infinity, right?
Right.
And so that's saying that those frames will eventually crash into each other. Is that correct? So in other words, if you take successive lines, successive, you know, and I hate to be, you know, you're saying that what we would have there is, instead of saying we'll make a table of lines that go, instead of, I mean, so the ordinary case of a frame with a given would be, let's say 0, let's see, we want the y direction, 0, y, and then x, let's say 10y or something, would be a table of that. Y goes from 0 to minus 10 or something. And then this would be our trivial motionless, what did I do wrong? Oops, graphics, not graph. What did I do wrong here? Line 0y. What on earth did I do wrong?
You did 0 to minus 10, so it's an empty value of y's.
Oh, good point. Okay, there's our frames, okay? Okay, so now a frame of a given velocity would be, presumably, this thing with 10 going from that y value there to this thing, 1.2 times y. Is that right? No, not right. Because what I want to do, I'm sorry, y plus a constant, plus 1.2. That thing I just did was more like the accelerating frame case. Is that correct?
Yeah, I think so.
All right. So is that right, in fact, that would be, let's say, 1.5y? Is that in fact?
Well, right, that's not a uniformly accelerating frame, right? A uniformly accelerating frame is going to generate like hyperbolas.
Right.
Because those frames don't crash into each other, so they have to go somewhere.
Well, so you're saying in that case, what we would have is a bunch of curves here where each curve has a derivative, hyperbolas or parabolas? What does it make? I mean, if it's uniform acceleration, normally, naively, it would be a parabola, right?
No, right? Because it can't, right? Because then it would eventually be going faster than light. Right.
You're saying an accelerated frame that if we take account of that we have to put in. I'm not Yes, I understand what you're saying. You're saying that we have to have something which has a square root of 1 minus beta squared in it.
Basically, yes.
Okay. We should probably wrap up here. We're way over time. But have people at least understood why I think this is interesting? No. Does anybody other than me find this interesting? Or does it
I find it very interesting to represent these various strategies or evaluation paths, which I've never seen before like this. So.
Yeah, I mean, I've been wanting to do this for 40 years. I just haven't, I've never found a way to think about this. I think that there are primitives for picking evaluation paths. We just don't know what they are. I had a version of them in SMP that nobody understood. The goal is to find a way to pick these evaluation paths that is understandable. All right, I'm gonna finish with this thing. This is these notes from Curry from 1927 about Schoenfinkel and combinators, and this is that's K, that's S, there's the S combinator, and there's the unfortunate thing. Let's see, correspond to the Sheffer formal stroke function. What the heck why is he talking about Sheffer stroke here?
Right, because aren't those what are they called? Shuffle algebras, right? So they're sort of, don't know exactly what the correspondence is, but.
Okay, the sad part of this story is, it says here, on discovery of this paper, I saw Professor Veblen. Schoenfinkel's paper said that's probably German, right?
Moscow.
In Moscow. Accordingly, we sought out Paul Alexandrov. Okay, I see. In Moscow, on Schoenfinkel's paper, right? The latter says Schoenfinkel has since gone insane and is now in a sanatorium, which is not a good outcome for, as the fixed point of working on combinators.
Mm-hmm. Well, that's sort of what happened to Cantor as well. So,
I know. This is the
territory.
Right. This is the problem, that when the abstraction level gets too high, it's hard to stay grounded, so to speak. Anyway, I mean, all right. Well, we should probably wrap up here, but I'm going to come back to this because I still think there's something really interesting here. I think that what we're going to come up with in the end is some way to define, which amounts to something like reference frames, to define to parameterize strategies for evaluation. And I think it's going to be I mean, I think there's going to be a calculus. For example, let's say we're connecting reference frames, right? We have a notion in, in the standard continuum general relativity, we have ways to think about connecting reference frames, although it's a bit of a mess with coordinate patches.
So is there some natural interpretation of, say, leftmost, outermost, or innermost?
I'm sure that there is. In terms of this, I mean, in this graph, right? In one of these graphs, leftmost, outermost is a path here. We just have to understand how to specify that path as one example in our parameterization.
So is there a way to uniformly specify that you always want the leftmost, outermost branch?
Well, undoubtedly, at a symbolic level, yes. But the question is, can we see what that means? I mean, I don't know. I mean, look, none of the things we have here, clearly what we've got here is kind of messy. We're picking out where the possible places to act are, and then we're, just doing a replace part at that place, right? So it's not a particularly convenient way to do this. Yeah, I mean, look, well, okay. All right, well, we should, this has made good progress. I mean, we haven't solved the problem, but I feel like this is good progress. Okay. All right. Well, we should wrap up here. I don't think we have not solved the problem yet, but so we'll be grinding on this some more, but we are making progress. All right. Thanks, everybody. And Jonathan, you and I have a different topic to talk about here. So if we can
sure.
Okay, all right. Thanks a lot. Thanks to folks on the live stream. I hope this was a bit abstract today, but hopefully of some interest. Thanks. Okay, see you all soon. Okay, bye.